A Linux system does not become secure because you installed a security tool. The easy failures usually happen earlier. A command runs in the wrong directory, an update is accepted without review, a service listens where it should not, or a file becomes writable by more people than the job requires. In this safe CipherVibe lab, we will not attack anything. We will use a fictional Ubuntu-style virtual machine called Cedar Lab and synthetic files called sampleauth.log and appconfig.demo. By the end, you will have a beginner routine: confirm where you are and who you are, inspect before you change, reduce unnecessary exposure, apply narrow access, and verify the evidence. That is the part of Linux security you can use before any advanced tool. Start with a disposable virtual machine from a supported Linux distribution. Keep the exercise inside an account and files you control. Take a snapshot before a change so you can return to a known state instead of trying to guess what a command changed. Our Cedar Lab diagram has one virtual machine, one regular learner account, one synthetic service, and one pretend authentication log. It does not point at a company network, a cloud account, or another person's device. The snapshot is not a replacement for backups or change control in real operations. It is a learning safety rail. In a real environment, use approved maintenance processes, tested backups, and written authorization. In the lab, the goal is to understand the decision before you automate it. The first routine is deliberately boring. In the Cedar Lab terminal, Huami confirms the effective account. PWD confirms the current working directory. Then ls-l-a lists the local lab files, including their owner, group, and access mode. Think of this like reading the address label before opening a package. A command can be perfectly spelled and still be wrong for the system, account, or path in front of you. Relative paths inherit your current directory. Privilege checks inherit your current identity. In our simulation, the expected answer is learner, home learner Cedar Lab, and a small set of synthetic files. If those facts do not match your plan, stop before you make a change. Context is a security control, not an introduction you skip once you feel confident. Patching closes known weaknesses, but patching is still a change. In our safe simulation, a package manager refreshes metadata from the distribution's supported repositories and presents a small review panel: packages to update, expected disk impact, services that may restart, and anything proposed for removal. The beginner habit is not memorizing one magic update command. It is knowing what the command will ask the system to do. Confirm the machine, read the package source, understand the scope, and schedule disruptive changes according to the system's role. Do not add random repositories just because a search result promises a newer tool. Mixed sources can create compatibility and support problems. Use the distribution documentation, trusted channels, and a lab snapshot when you are learning. After an approved change, check that the intended service still works and record what changed. A network listener is a program waiting for a connection. That does not automatically mean danger. It means you should be able to answer a few questions: which process owns it, who needs to reach it, which interface it uses, how it authenticates, and where its activity is logged. In Cedar Lab, a simulated SS-tone view shows one expected local web service and one unexpected test listener. We do not scan anything. We simply inspect our own machine's listening sockets and compare them with the lab's intended design. The correction is not block everything and hope. We remove or disable unused services through the approved system method, and we keep a host firewall policy that permits only the necessary traffic. A small, explainable exposure is easier to patch, monitor, and recover than a collection of forgotten listeners. Linux permissions are not one global setting. A mode string separates the owner, the file group, and everyone else. Each class can have read, write, and execute access. For a directory, execute controls traversal or search, so it does not mean exactly the same thing as execute on a normal file. Our lab starts with an intentionally broad synthetic configuration file. The diagram marks the excess access in amber. We state the real requirement: the learner account may read and update it, the group may read it for review, and everyone else needs no access. The important habit is the sequence: inspect owner and group, state the requirement, apply the narrowest understandable change in a disposable workspace, then inspect again. Do not use broad permissions as a repair shortcut. Ownership, access control lists, mount options, and mandatory policy can also matter, so a successful command is not proof that the access design is correct. Use a regular account for ordinary work. When a task legitimately requires elevation, make the elevated action as small and clear as possible. Before you approve it, reread the command, the options, the exact path, and the expected result. Our simulation contrasts two choices. The unsafe card says run an unknown downloaded script with full privilege. The safe card says inspect a known local configuration, make one approved change, and verify it. The safe card is not exciting, but it contains scope, ownership, and a recovery path. Never elevate merely to silence an error you have not understood. A permission problem can reveal a wrong target, broken ownership, missing policy, or an application design issue. Turning everything into root access expands the blast radius and removes the evidence you need to understand what is actually wrong. Now we use the fictional sampleauth.log. First, we confirm its location and make a working copy inside the Cedar Lab evidence folder. The original remains untouched. We then filter for the word failed, review the small result, and write a clearly labeled summary into a separate output directory. The key point is interpretation. A failed authentication line is an observation, not a verdict. It could be a typo, an old service configuration, a test account, or something that needs investigation. Add time, identity, source, asset purpose, and corroborating events before you claim more than the evidence supports. In real security operations, protect logs from unauthorized modification, centralize the events you need, synchronize time, and follow your incident procedure. In this local lab, you are practicing the order: preserve, inspect, explain the limit, and document the result. The fastest way to create a Linux problem is to paste a command because it appears in a comment, forum answer, or video. Before you run a command, explain the target, the privilege level, where the input comes from, what output it changes, and how you would recover if the result is wrong. Our simulated terminal shows an opaque command stopped by a review gate. The gate asks, which files will this touch? Does a wildcard expand to more than one item? Will output overwrite an existing file? Does it contact an untrusted source? Does it run with elevated authority? If you cannot answer those questions, the secure action is to pause. Look up the supported manual page, test the smallest version in a disposable lab, or ask the system owner. Linux confidence comes from being precise, not from making the prompt disappear quickly. Here is the routine to keep. First, confirm context, the machine, your identity, your directory, and the object you intend to inspect. Second, use supported update channels and review a proposed change. Third, map listening services to an owner and a purpose. Fourth, make file and privilege access as narrow as the task allows. Fifth, preserve and interpret evidence before you draw a conclusion. This is not a certification checklist or a promise of perfect security. It is a way to turn beginner curiosity into safe, repeatable operations. Practice it in a virtual machine with synthetic files. Take snapshots. Explain every command out loud. Make one small change, verify it, and write down what happened. That is how a Linux terminal becomes a security tool, not because it looks powerful, but because you use it with context, control, and authorization. Find the full Safe Lab checklist at CipherVibe.com/blog.